Okay, so let's look at some other alternative methods to calculate this vector potential. You see, we know that A dot ds, the integral of the vector potential around any closed surface, this should be equal to 0. Well, it's just like the magnetic B field, B dot ds integrated over a closed surface was also equal to 0 all the time. Well, this just states that the A field lines corresponding to A, they cannot start or end at a given point, at any point. So they have to either form closed loops or they have to start from infinity and go to infinity. And furthermore, we know that A dot dl should be equal to B phi B. This is the other condition we have. Now let's look at our solenoid example again with this perspective. This is my solenoid. Let's assume that the current is running in this direction, so the B field is homogeneous and pointing outside. This is our B field. This is the z-axis. B is equal to mu0 n times I in the z-axis if S is less than the radius of my ring, of my solenoid. And again, we will be looking for a vector potential of this form, AS in the phi hat. Well, let's consider such a circle. Let me consider this circle. Then A dot dl around that closed loop, let's say it has a radius S. A is AS in the phi hat direction. What is dl? No, dl. The dl cannot be Ps. dl is an infinitesimal vector. What is dl vector? It has its magnitude, let's call it dl. Well, it's phi hat or minus phi hat? You see, this is our z-axis, so phi hat is counterclockwise. So it is in the minus phi hat direction. So this is equal to minus AS times the integral of dl is now 2 pi s. Now you're right. Now what about the magnetic flux? B dot ds. What is the direction of ds? This is B is mu0 n times I in the z direction. ds vector is ds in the which direction? Z or minus z? Because my loop is clockwise. So ds is in the minus z direction. This is equal to minus mu0 n I times pi s squared. And since A dot dl should be equal to the magnetic flux, AS times 2 pi s should be equal to mu0 n I times pi s squared. Or A of s should be equal to 1 over 2 mu0 n times I times s. Well, this was the result that we had obtained previously. Well, let's calculate A outside. Now, to calculate the A outside, I will assume such a loop. And just repeat the same thing. A dot dl. A will be AS in the phi hat direction. dl is dl in the minus phi hat direction. So this is minus as times 2 pi s. Again, I just call the circumference s. This is s. This time s is larger than the radius of my ring. On the other hand, the magnetic flux is b dot dl. But keep in mind, sorry, not dl, b dot ds. B is non-zero only in this region. It is 0 over here. So I can divide my surface integral, my area integral, into two parts. Over this ring, over this disk, which coincide with the interior of my solenoid, and over this ring outside my solenoid. There is no contribution from outside my solenoid. There is only contribution from inside, so the total flux will be independent of S, and it will be given by mu 0 n times I times pi r squared. Of course, again, in the minus direction, because since my loop goes in the clockwise sense, my area vector should be in the minus z direction. But my B field is in the plus z direction. And hence, we have from the equality of A dot dl to B, we have AS 2 pi s should be equal to mu 0 n I times pi r squared, or A of s should be equal to 1 over 2 mu 0 n I r squared over s. This is the other means of calculating A. Well, the trick is how do you calculate the B field, the flux. As long as you can calculate the flux, and as long as you have sufficient symmetry in your problem so that you can say that A has such a simple form, then you can use this.
Why did we choose the direction of Gaussian surface?
Not Gaussian surface, this is the Amperian loop.
Sorry. Why did you choose the direction clockwise? Why not counterclockwise?
Let's choose it counterclockwise and repeat the calculation. Let's see what will happen. So we do the same treatment for the same loop. The only difference would be that instead of going clockwise sense, we will go in the counterclockwise sense. A, the vector potential, is AS in the phi hat still. I'm not changing the definition of the vector potential. Now A dot dl, this will be equal to AS phi hat. Now dl is also in the phi hat direction. So times dl in the phi hat direction. So S is constant, so A of S, I can take it out of the integral. A of S times 2 pi s. Now compare it with the previous case, A dot dl integral was minus AS times 2 pi s. So since I changed the sense of my loop integral changed its sign. So that's kind of expected. It's just like changing the order of the limits in a one-dimensional integral. Now the B, it will be again mu 0 n times I. This is the B field. It's only in the region inside my solenoid, which has an area pi r squared. Now this time it's a positive flux because ds is in the z direction, B is in the z direction. So this is also positive now. So AS times 2 pi s is equal to mu 0 n times I pi r squared, or A of S is equal to 1 over 2 mu 0 n times I r squared over S. Exactly the same result with the same signs. So the result is independent of which sense you choose for your loop, as long as you are consistent in your derivation. You see, this is the relation we have. A dot dl over any closed loop, this is equal to B dot ds over the area bounded by the loop. So here I have a ds vector, here I have a dl vector. These two have to be consistent. That means they should be related by the right-hand rule. Well, you are free to choose the direction of dl. If you change the direction of dl, that automatically causes a change in the direction of ds. So a relation still holds no matter which direction you choose for dl. It's your choice. You can choose the direction of dl. Any direction is fine.
In the previous case, why was ds in direction of minus 10?
In this case, ds was in the minus z direction, because the sense of the loop tells us what should be the sense of my area, or the sense of my area tells me what should be the sense of my loop by the right-hand rule.
Hocam burada vektör potansiyel fiziksel bir anlam bu iş.
No, it's just how, I mean, the question of whether the vector potential is a physical quantity or not is not a trivial question, especially when you take into account quantum mechanics. I mean, when you take quantum mechanics courses, you will study an effect called the Aharonov-Bohm effect. So is the vector for potential, does the vector potential have a physical significance beyond giving our B field? You see, especially in this problem of the solenoid, outside there is no B field. But outside still the vector potential is not zero. There is a vector potential, but no B field. So if vector potential can affect a physical phenomena, then that phenomena should occur even outside the solenoid, even if there is no magnetic field. And in quantum mechanics, at least, we do have such phenomena. The particles do not enter into the region where there is a magnetic field. Nevertheless, they feel the existence of that magnetic field because the vector potential is non-zero outside. Anyway, that is something you will study probably in graduate study.
Hocam bir de burada elektrik alan var diyor.
There's no electric field, there's just a B field.
Ama akım var ya yukarı.
Well, it's neutral. It's a wire. Think of the wire. There's no electric field. Well, of course, you can think of, for example, for a solenoid, instead of thinking of a cylinder with wire wound around it, you can take a cylinder which has a uniform surface charge density and rotate this cylinder around its axis. In that case, this is both a problem in electrostatics and also magnetostatics. So inside this solenoid, we have a magnetic field, B field generated, which will be uniform. Of course, you have to identify what is I in this case. Inside, there won't be any electric field because you have your cylindrical symmetry. Just use the Gauss law. Inside, the electric field is zero. The electric field is only outside. Since the charge density is not changing in time, still this is an electrostatic problem, although it's a rotating cylinder.
Hocam o silindir böyle dönüyor ya. Onu aniden durdursam.
That's no longer static.
O zaman yükler yine değil.
That's no longer static. So what do you mean by a cylinder? Maybe it's just the charges. So if you say you stop the charges, you stop the cylinder. Well, not a bad midterm problem. Not the last question, but the previous one. A charge rotating cylinder. Okay, any other questions on this one? Well, your friend wanted to discuss this problem of a well, we have this disk, well, it's not disk, sorry, a sphere with a uniform surface charge density, the radius is r, and it is rotating with an angular velocity omega pointing upward. Well, we can choose that direction to be the z direction. So what is the vector potential, what is the B field, etc.?
The sphere or it's just a disk?
It's a sphere. So you just take a ball, on the surface there is a uniform surface charge density, and you just let it rotate. Then what is the vector potential, etc.? Now, rather than calculating the vector potential directly, let me calculate the magnetic field in kind of a different way. So what do we know about the magnetic field? Del dot B is equal to 0. Curl of B is equal to mu 0 times J. Well, the J is only on the surface of my sphere. There's no J anywhere else. Well, this tells me that curl of B is equal to 0 both inside and outside the sphere. You see, curl of B is non-zero on the sphere. Everywhere else it is 0. Well, you see, what we were doing about the magnetic field in general, the divergence of B is 0. And hence, using this fact, we said that B can always be written as the curl of a vector potential. But in this problem, it's also the curl of B is 0, almost everywhere. But if the curl of a vector field is 0, remember electrostatics, curl of the electric field was 0. So here the curl of the B field is 0. So B can also be written as the divergence of a scalar function. Because curl is 0. Of course, I can write this outside the sphere. I can write this inside the sphere. I cannot write this on the sphere. Well, I don't really care. You see, I can write this outside the sphere, I can write it inside the sphere, solve them, and just match the B field both inside and outside. We will see. Well, we don't know whether phi is continuous. You see, it shouldn't be continuous, because if it was continuous, then I can always talk about this gradient. But I shouldn't be able to talk about its gradient on the surface because it shouldn't exist on the surface. But we will see. But at least both inside and outside, I can always define such a phi m, magnetic scalar potential. Well, if this is the case, del dot B is now minus the Laplacian acting on phi m. This should be 0, or phi m satisfy the Laplace's equation. Okay, this is nice. So we already have discussed how to solve the Laplace's equation in spherical coordinates. You see, I have a problem which doesn't change as I rotate around the z-axis. So nothing should depend on the phi coordinate. It can only depend on the distance from the center of the sphere and also on the theta angle and nothing else. We had already discussed such problems in electrostatics, and we know that if we are looking for a solution of the Laplace equation in spherical coordinates, which doesn't depend on the phi coordinate, then the general solution can always be written in the form AL times R to the L plus BL over R to the power L plus 1 times PL of cosine theta. Well, this will be kind of a reminder about electrostatics, which is also included in the midterm. So this is the general solution of the Laplace's equation in spherical coordinates. This is the general solution for a solution that doesn't depend on phi. And we know that in our case, the phi should be independent of in our system, phi should be independent of the phi coordinate because nothing changes if I rotate my system around the z-axis. Well, let's see. Phi m. Now, I have two regions, two separate regions, inside the sphere and outside the sphere. Let me say, call inside the sphere region 1, outside the sphere is region 2. In region 1, I have the point r is equal to 0 is in my region 1. So in region 1, the scalar potential, the expressions of the scalar potential at r is equal to 0 should be finite. It should be finite. But if it is to be finite, then these b terms, they diverge at r is equal to 0. So inside, I cannot have those b terms. So phi m of 1, phi m in region 1, which is a function of r and theta, should be written in the form AL r to the L PL of cosine theta. So this is one condition I have. Well, this is the solution inside my sphere. Well, I still need to determine those ALs. In region 2, I have the point r goes to infinity. Well, if I am very far away, I can choose my potential to be 0. But this tells me that AL terms should be absent in region 2. I can have BL terms, but not AL terms. So phi m2 of r theta should be in this form. BL over r to the L plus 1 PL of cosine theta. Okay, so these are the general solutions both inside my sphere and outside the sphere. Well, I don't know whether phi is continuous or not. So I would rather not use the continuity of phi or any continuity of its derivatives. But I do know certain conditions. Like, I know that the divergence of B is equal to 0. But if the divergence of B is equal to 0, this tells me that the perpendicular component of B is continuous, perpendicular to the surface. You see, if you remember in electrostatics, we said that the perpendicular component of the electric field to a surface can be discontinuous, and the discontinuity is proportional to the surface charge density. There's no magnetic surface charge density. So you see, the right-hand side is 0 all the time. So the perpendicular component of B is always 0. Well, our problem is a sphere. The perpendicular component is the radial component. So this tells me that BR is continuous. Well, BR is nothing but minus the derivative of phi m with respect to r. This is the radial component of B. So the radial component of B in region 1, sorry, this is region 2. In region 1, the first line is my scalar potential. Just take its radial derivative, multiply it with -1. That's the radial component of my B field in region 1. And that gives me minus sum over A L times L R to the power L minus 1 PL of cosine theta. This is the radial component of the magnetic field inside my sphere. I can also calculate the radial component of the B field outside my sphere. This is equal to, well, the potential outside my sphere is given by that expression. Just take its derivative, multiply with -1, and you get this is equal to L BL over R to the L plus 2 times L plus 1 times PL of cosine theta. And on the surface of the sphere, these two radial components have to be equal because the divergence of B is 0. And this tells me that sum over L minus A L L R to the power L minus 1 multiplied with PL of cosine theta. This should be equal to sum over L BL over R to the L plus 2 multiplied by L plus 1 PL of cosine theta. Well, Legendre polynomials, they are complete, they are orthogonal. So if you have any such equality involving Legendre polynomials, then the coefficient of the corresponding polynomials have to be equal. So the coefficient of PL cosine theta on the left-hand side should be equal to the coefficient of PL cosine theta on the right-hand side. And that gives me one set of equations between these two unknowns A and AL and BL. So minus AL times L R to the power L minus 1. This should be equal to BL over R to the L plus 2 times L plus 1. So this is one condition I have for these coefficients ALs and BLs. This condition I obtained by looking at the divergence of B. And the divergence of B was 0, which allowed me to conclude that the component of B perpendicular to any given surface has to be continuous as you are crossing that surface. Now we also have another property of the B. The B should satisfy the property that the curl of B should be equal to 4 mu 0 times J. Now let's see what this property tells me about the components of B, how the components of B change from point to as you cross a surface. Now if you remember, in the case of the electric field, we knew that the curl of the electric field was equal to 0, and so we considered, given any surface, we considered such a loop over the surface, such that one part of the loop is on one side, one part is on the other side, and we just studied B dot dl. Well, in that case, it was E dot dl. E dot dl integrated over the loop was 0. Well, in this case, B dot dl integrated over the loop will be just mu 0 times the total enclosed current in the loop. It won't be 0. Well, the current is running in a given direction. If there is a surface current, it will be running in a given direction. So basically, when you are choosing this loop, you can choose this loop along your current. Let's say the current is running in this direction. You can place your rectangle in this form. The current is parallel to your rectangle. So the enclosed current will be 0. Or you can place it in this form. So this is the direction of the current. The current is running through your rectangle. Enclosed current will be non-zero. And we will need to study both cases. Now, first, let's consider the case in which This is the direction of the surface current. In this case, for this loop, I enclosed is 0. Let's say this is D. Below the surface, the distance is also D. B dot dl over this loop, which is parallel to my current, in the limit as D goes to 0, let me choose this direction as the k hat direction. This is that's the direction in the direction of k. So this will be, and let me call this the n vector. This is outside my surface. This is inside my surface. So B outside minus B inside in the k hat direction. Let's say this, the length is h times h. This should be equal to mu0 times I enclosed, but the enclosed current is 0. No my loop is parallel to the current, so there's no current passing through it. So I can just cancel the h, and this tells me that B outside minus B inside in the direction of the current is 0. So we already know that the direction of B perpendicular to my surface is continuous as I cross the surface. B also has a component in the direction of my current, surface current. The component of B in the direction of the surface current is also 0. It is also continuous. It is change as you cross the surface is 0. So there is only one component that we need to study, the component perpendicular to K. So this is my surface. This is my N. Let me assume that I just rotated my surface such that K is into the screen. This is my K. I will again assume a similar loop such that half of it is on one side, half of it is on the other side. Let me call this length h. I will go around the loop, let's say in this sense. And k is inside. Let me call this direction my m hat direction. So basically at this point, I have 3 vectors. Just like the 3 components, 3 coordinates. I have the perpendicular direction, perpendicular to K, to the surface, and on the surface I have the direction of K, and I have the direction perpendicular to K. So these are my 3 axes, 3 perpendicular axes. I already studied how the 2 components of my B field change as I cross my surface, the component in the direction of N, the component in the direction of K. Now I'm just looking at the component in the direction of M along my surface. So B dot dl around this loop will be B outside minus B outside plus B inside. Well, why minus B outside? You see, I will B outside. This is now DL is pointing in the minus M direction on the outside. DL is pointing in the M direction on the inside. So that's why I have that minus in front of the outside B. Scalar product with M multiplied with H. This is my B at dot DL. Well, I'm skipping several steps in this result. Assuming you are already familiar with this, we did this derivation a couple of times before, but if you want me to repeat, I can repeat how do I obtain this one from this line integral. So this is, of course, in the limit as D goes to 0. So there's no contribution from the sides. There's only contribution from the parts of my rectangle that is parallel to my surface. And this should be equal to the total current running through my loop. There is a surface current. Well, surface current means that the current per unit length. The total length in my loop is H. The current per unit length is K. So I just multiply K and H to obtain the total current. This is mu 0, K times H. But keep in mind the direction is minus. You see, my loop is going counterclockwise. Use your right hand, the positive current is out of the screen. But the current is into the screen. So that's why I should put a minus over here. And now the H, I can cancel the H's. I obtain B outside minus B inside in the direction of M should be equal to mu 0 times K. Now let us combine all of these. Let me write B outside minus B inside. The jump in the B field as I cross my boundary. And remember, I'm crossing my boundary at this point, and at this point I already have my 3 coordinate axis chosen. There is a component in the direction of n. In the n hat direction, where it is just 0, we said that the component perpendicular to the surface is continuous. So in this difference, they just cancel each other. So it's just in the n direction, I have 0. In the k hat direction, we also said that the change in B in the k hat direction is also 0. And the final one is in the m hat direction. And in the m hat direction, we calculated that this difference is just mu 0 times k. Or this is equal to mu 0 k in the m hat direction. But let's see, m hat direction is nothing but n, k cross n. This is equal to mu 0 k, k hat cross n. This is my m hat direction. You see, k hat is into the screen, n is in that direction, k hat cross n is in the m hat direction. It's just like if you have 3 perpendicular axes, x, y, z, x cross y is in the z hat direction. X hat cross y hat is z hat. So we have B outside minus B inside should be equal to mu 0. Well, I have the k vector multiplied with the k hat, now k magnitude multiplied by k hat. This product is nothing but my k vector cross n hat. So if you have a surface current, the magnetic field, the B field, it changes continuously across this surface, and the discontinuity is given by the direction of k, the direction of n, mu 0 times this cross product. This is the surface current density. Now we can use this. We will be using this in our problem. So we know what B inside is, we know what B outside is in terms of these unknown coefficients A's and B's. So we can basically calculate this one in terms of A's and B's. If we can write this explicitly, then we know what we will be able to obtain another relation between A's and B's. We already have one set of equations between A's and B's. This will give me a second set of equations between A's and B's, and I will be able to solve them. Now, the critical thing will be, what is K in our problem? The surface current.
Çünkü şey sorayım. Hani E ile B arasındaki ilişki biliyoruz dediniz ya.
Okay.
Şuradaki D manyetik alan mı yani?
Where? This is one relation we have. No, this B, no, okay. Some bad notation. This BL are the coefficients appearing in the expansion of phi m outside my sphere. So I don't know BLs. I don't know ALs. Those are things I'm trying to determine. And to determine them, I'm just trying to find some relations between the two. This is one relation I obtained by the continuity of the perpendicular component of the B field. And now I will be using the discontinuity of the horizontal component of the B field. You see, since n is perpendicular to the surface, k cross n is always parallel to the surface. So the discontinuity is only in the parallel component of the B field, if any. Now let's look at what k is. Well, you see how we define k. K is the current per unit length. That is how we define the surface current density. So let me assume a length over here, dl. Well, that length will correspond to a ring on my sphere. So if I wait one full rotation of my sphere, all the current in this ring will pass through my dl. So what the total charge on that ring? So that is the first thing I have to study. If I can find the total charge, then I need to determine the time it takes for all that charge to pass that line segment. I divide them. I get the current running through that line segment. If I divide that current by dl, I get the current per unit length, which is my surface current density. Now, first of all, if I open that ring, it is basically a rectangle with the long side given by, you see, this is r. If we call this angle theta, this length is r sine theta. Now, the area of that ring is 2 pi r sine theta. This is the circumference of the ring. If I multiply it with the thickness, this is the total area of the ring. If I multiply by the charge per unit area, sigma, this is the total charge of that ring. And all that charge passes through this dl in a time in one full rotation, but one rotation takes an amount of time 2 pi over omega. This is the current running through that very small segment. But by definition of the surface current density, this is just k times dl. So that basically tells me that k is equal to omega r sine theta times sigma. This is the magnitude of k. What is the direction of k at that point? Well, at this point, let's say it is into the screen. Well, that is the direction of omega cross r. But omega r sine theta is nothing but the magnitude of omega cross r. So this is omega cross r in the sigma times sigma. Well, if you remember circular motion, omega cross r or omega r sine theta is nothing but the speed at that point. Omega cross r is just the velocity at that point. So the surface charge density is nothing but the surface charge multiplied by the velocity. Well, you see, k is omega r sine theta times sigma in the phi hat direction. phi hat is into the screen. You see, at this point, phi hat is into the screen. This is my r hat. This is my normal vector, which is nothing but r hat. So k cross n. What is the direction of k cross n? K cross n is this direction, which is nothing but theta hat. You see, k is into the screen. This is the k. N is this direction. K cross n is somewhere in that direction. That is my theta hat direction. That is the direction. If I move in that direction, I do not change phi, I do not change r, I only change theta. So that's why we call it the theta hat direction. So k cross n is equal to omega r sine theta sigma in the theta hat direction. So this tells me that B outside minus B inside, which was we had obtained before that it has to be mu 0, k cross n, this has to be equal to mu 0 r sigma sine theta in the theta hat direction. Well, this tells me that it's only the theta components of B that is discontinuous. Now, that's not a great surprise because we started with a scalar potential phi m, which doesn't depend on phi. So basically, the phi component of B is 0. 0 inside, 0 outside, so it's continuous. But the theta component, since there's a surface current, turns out to be discontinuous. So let's look at the theta component. B theta outside minus B theta inside should be equal to mu 0 r times sigma sine theta. Well, B theta, let's say we already calculated phi in region 1 inside our sphere, in region 2 outside our sphere. So B theta in spherical coordinates, this is nothing but 1 over r d phi m by d theta. So in region 1, no, sorry, this is r. This is minus 1 over r del by del theta. Our potential phi m in region 1, that is inside our sphere, is just al r to the l pl of cosine theta. This is equal to, so B theta inside, you see inside is inside face of our surface. So it is when small r is equal to the radius r. So this is equal to sum over L of minus AL r to the power L minus 1 times d by d theta PL of cosine theta. This is B theta inside. Now B theta in region 2, that is outside my sphere, we had already seen that this is minus 1 over r del over del theta. Our potential in region 2 is BL over r to the L plus 1 PL of cosine theta. And B theta outside, this is equal to sum over L minus BL over capital R to the L plus 2 del over del theta PL of cosine theta. No, I'm not taking the derivative with respect to L. I'm taking derivative with respect to theta. So that's why I don't have this L plus 1 or L plus 2 factors. In my first relation, I do have those factors. In this one, I don't. Well, I just need to subtract the two, B outside minus B inside. And that would give me sum over L, AL r to the power L minus 1, minus BL over r to the power L plus 2, times del over del theta, PL of cosine theta. This should be equal to mu 0 r sigma sine theta. There should be an omega somewhere. Well, you see the left-hand side is a derivative with respect to theta, so let me write the right-hand side as a derivative with respect to theta also. This is minus mu 0 omega r sigma d by d theta of cosine theta, which is minus mu 0 omega r sigma d by d theta of P1 of cosine theta. P1 of cosine theta is just cosine theta. That's what I'm using. Well, we know that PL of cosine theta is, they are complete set. They are orthogonal to each other. So if two sums of PL of cosine theta are equal, their corresponding coefficients have to be equal. Well, the same holds for their derivatives. If you want, you can just integrate both sides. Get rid of the theta derivatives. So the coefficients of the derivative of PL of cosine theta with respect to theta on both sides should be equal. So let's see, for L is equal to 1, on the left-hand side, the derivative of P1 of cosine theta, the coefficient is A1 minus B1 over R cubed. This is the coefficient on the left-hand side. On the right-hand side, the same coefficient, the coefficient of the derivative of P1 of cosine theta is minus mu 0 omega r sigma. This is for L is equal to 1. For L different than 1, the coefficient on the left-hand side of PL of cosine theta is AL, r to the L minus 1, minus BL over r to the L plus 2. And the coefficient of PL cosine theta on the right-hand side for L different than 1 is 0. There's only P1. There's no other PL. So this is 0 on the right-hand side. Now this gives me my second set of equations for these coefficients A and B. Remember, before I obtained this condition between A and B, whether L is equal to 1 or not. Now I have this other condition. Now first we can solve for ALs and BLs if L is different than 1. You see, if L is different than 1, I have this equation which tells me that AL and BL, they are of the same of different signs. You see, I have BL, all of these are positive. BL should be some positive number times minus AL, so which tells me that AL and BL, they are of opposite signs. But if you look at this above expression for L different than 1, this tells me that AL and BL, they should be of the same sign. Two constants can be both of the same sign and of the opposite sign only if they are both 0. So I already know the solution for AL and BL if L is different than 1. So although I started with a potential that had infinitely many terms, at the end it turns out that only one of the terms is non-zero. All the other terms are 0. Okay, then you can just find the A1 and B1 to determine your phi m. So I will not do that. They're about to kick us out.
For L is not equal to 1, why is R to the power L plus 2 in denominator?
We are here. Just look at the derivation. We have this 1 over r factor multiplying the, you see, when we are taking the gradient of phi m, the theta component is the derivative with respect to theta multiplied with 1 over r. So the BL was r to the L plus 1, the coefficient. If I divide by r, it just becomes r to the L plus 2.